Okay, another test. This is another test. This is another test. Okay, another test. This is another test. This is another test. Okay, another test. This is another test. This is another test. This is another test. Still quite low, right? This is another test. This is another test. This is another test. Still quite low, right? This is another test. This is another test. This is another test. Still quite low, right? This is another test. This is another test. 1, 2, 3. Still quite low, right? This is another test. 1, 2, 3. Still quite low, right? This is another test. 1, 2, 3. Still quite low, right? 1, 2, 3. Still quite low. 1, 2, 3. Still quite low. 1, 2, 3. 1, 2, 3. Okay, Test. Jetzt mal Mitschallschutz. 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 Okay, hello and welcome to SQL TV. Okay, hello and welcome to SQL TV. Okay, hello and welcome to SQL TV. Okay, this is just an audio test in the beginning. Okay, it's quite fine. So let's just start my equipment here. So let's just distribute the news that we are live right now. So let's just please wait 1 second. We were starting very soon. We'll just put it out on Twitter that we are live right now. So I just basically need a web copy video or URL. That will be it. Okay, let's go on to Twitter and spread the news, and then we will start with our stream. So let's just spread the news, tweet. Okay, then just share it, and then we can start right now. I will of course cut this out in the final VOD. Let's just spread this spread this here. Spread it on Facebook, all the beautiful social media. Just come to SQL TV, and we are live right now. So good to go almost, I hope. Okay, so now that's it. So hello again, folks, this time with another format of SQL TV. Normally I upload videos quite regular, let's say like this, to YouTube. This time I decided to try something new, since I actually like the concept of streaming very much, and I don't have so much time for pre and post production at the moment, and I still want to do some content. I thought, why not just do a live stream, just fix the camera a little bit, and I mean, you can also see it as a VOD. I will probably edit it a little bit afterwards, just cut out a few scenes where I do tests and stuff, but basically you can also watch everything later on. So for our test setup today, we want to talk about graphical execution plans and how we can read those actually. So you know, this will be a web series. If this is more or less successful, or if there are no complaints at all, I will probably, if there's no negative feedback, continuing on doing videos normally like I did before with on the whiteboard, with post-production, pre-production, and so on and so forth. But I also consider to do this web session where I can talk about graphical execution plans and how to read them, and I mean, there's quite a lot to handle here. We can also do something more lab-like here with my Visual Studio right in place. Where is it? Here it is. So we can actually see what we are doing. Yes. So we just start with graphical execution plans. Let's just start right away. I mean, if there's anybody tuning in, we can still you can use the chat here, and we can just focus on your questions and on your wishes. That's no problem at all. Actually, I very much like to have interaction with the community, so if you feel like you want to connect to me, no problem, just state in chat what is your question. It doesn't really have to be related to this topic. I can also talk about it, and I can cut the final edit of the VOD later. This is no problem at all. Okay, so let's just get my windows arranged here so I can see everything what's going on, and then let's just start with the actual content. So graphical execution plans in SQL Server, or better in SQL Server Management Studio, are actually a nice feature. You can see how the query that you wrote is actually executed on the engine of SQL Server. So we will just start with a few properties here. I didn't prepare anything for this. I just prepared those little presentation, and I hope everything will be fine. So let's check it out. First of all, we have shortcuts. This is Control L for estimated query plan, and Control M for the actual plan. But we will come to this in the lab session very soon. So let's get started here. So yeah, as I told you, it gives you a good picture of what's about to happen, what is going to happen in the query itself. You have the estimated plan and you have an actual plan. They can differ. Mostly they are the same, just including actual row numbers that you can only find, of course, in the actual plan. May, of course, differ from your estimated row numbers, from your estimated cardinality and stuff like that. But normally, if you don't have big recompilations with the plan, the estimated and the actual plan are quite the same, at least visual wise, not data wise, what is flowing there. Then you also see here, as I told you, recompilation may change the estimated plan. This is actually an XML file with a lot of more information than you can just see from the Management Studio. We will see in a few minutes. So I just talked about textual plans. Are there also other plans? Yeah, of course. You have also there are of course textual plans. And as you can see in this little view, we have textual plans we can get with different commands like set show plan text on will not execute the query, won't include estimated stuff, and won't include actual row counts, and just the show plan as a text form. Then the show plan all will do the same thing, but just include estimated row counts instead. And the set statistics profile on will also execute the query and bring detailed plans with, of course, also actual statistics, because it executes the query. We have basically almost the same for XML plan. We can say set show plan XML on, we get just an estimated query plan, and with set statistics profile, basically like here, but XML, we can see everything since it gets actually executed. Yeah, so let's just jump to the Management Studio and do a little exercise on this. So we are here in the Worldwide Importers DW database, which you can also find online, of course. It is the new AdventureWorks sample database that is provided. So let's just check this out. So we have here a dimension. Okay, we have mostly. Let's check out what we have in here. So as you can see here, we have mostly facts, as you could think of it, as in data warehouse, and we have also, of course, dimensions for data warehouse. This is all we need right now. We just focus on the dimension customer. Let's just select real quick. So we have here a customer key. That is the primary key. Then we have maybe an alternative ID key here, and then we have some attributes here. Okay, so it's a very simple table. You don't need to know too much about it, and yeah, we can now hit Control L, and we see here basic plan. Very basic. We see here a node. This is called clustered index scan. Cost 100% because there's no other node here but the select node, which is just the root node of this tree. Nothing fancy we can see here. Let's just jump to the presentation. I want to inform you that you have to read those plans always from the right to the left, and if you have many more on the right at the same column, then you have to read from the top to the bottom. So in our case, we have just one node here. We would read it from the right to the left and from the top to bottom. Okay, but for our example here, it's pretty much straightforward. We just have one node, so it is just a cluster index scan involved here. So why can't I just, okay. You can see also interesting like parameters in the query, like the degree of parallelism. That means how many is it a multi-threaded plan execution, or is it a serial plan execution, and if it's has multiple threads involved, what is the degree of parallelism. And we also have some memory information, what is actually requested the memory for this query, what actually granted memory if we see the actual query then, and the compile time and memory that the plan itself needs. So we find this we find all here on the right hand side. We can, for instance, see this is compile CPU 0, so compile memory, it only takes 696. I think this is kilobytes. There's an estimated number of rows. We expect around 403 rows. Yeah, then we have also memory grant info, which of course is 0 here, since this operation does not need any memory. And we have also the degree of parallelism. I think we can only see this if we execute it. So we hit Control M and we execute it, and then we go to the actual query plan. Then we see here much more stuff. Here for the query, we see the degree of parallelism is 1. As you can also see on the plan, there is no multiple threads involved here. So here you can also see memory grant info. Again, it will be 0, of course, since clustered index doesn't take any memory. And if maybe some of you are now tuning in, as I told you, we are talking here about how to read graphical execution plans. But of course, it's a live stream in the end, so if you have any questions, you can raise those questions, of course, and we will also I will of course answer them if I can, and the VOD will of course only have the information that we need for our video, but the live stream, I'm fine with any questions, of course. So this is basically a starting point where you can also see, okay, what is my query doing? It is doing a clustered index scan, obviously, and it has some basic information like how many threads will be involved, how many memory will be involved for this query, and much other stuff. So we don't need to focus on this right now. It's just an overview for us. Okay, so then let's come to the first two operators. We saw here we can retrieve data for a clustered index, and this is a clustered index scan. And we also have another operation that is called a seek. Basically, we have only those both types of data retrieval. This is a scan, and the other thing is a seek. So if you notice this here, this is should be a B tree. So this could be our clustered index where the data is actually stored. We have two possibilities for this clustered index to access data. The first one is a scan. What a scan would do, it would go to the leftmost leaf page, which will be, in this case, we take always the leftmost pointer. We would start with this page, and then we would go sequentially, consecutively, always following the next pointers of the pages. You get the idea, and we run linear through all the leaf pages. This is basically the equivalent also of a full table scan, but in SQL Server it's just called a clustered index scan, meaning it scans all the leaf level from the top left, from the most left to the most right position. A seek is different. A seek really makes use of the B tree to find the actual path and access only the data files, the data pages that you want to have. For instance, if you know your clustered index is put on an ID column and you are looking for only entries from ID 20, or in this case it is with numbers, it would go, okay, let's go here, okay, I need this path now, okay, here is my data. So we don't need to go through all the pages here. We can just have two data accesses, two IO accesses, and we get the data straight away. Of course, the seek is can be much faster, and the scan reads always all the data. So let's come to a few examples for this. Let me see what we have right here. So we just talk. The first thing is we talk about an index scan. So for a clustered index, it's called a clustered index scan, and for a non-clustered index, it's just called index scan. But nevertheless, the icon is always the same. You see this icon here, it suggests that you go first to the bottom, and then you run straight to the right, and scan all of those leaf pages here. So actually it suggests already what will happen. I told you it's also known as a full table scan. It is mostly used when you have no where condition in your query, or it is used when you have where condition that is not part of your index key. Of course, then it cannot be used on the B tree if the B tree only consists of, for instance, on the first name, and you have in your where condition the salary, and the salary is not present in this index. Of course, the index can't be utilized, so then we can just use a clustered index scan in this case. It also only applies where the condition applies to most of the rows, because then the scan is cheaper than to seek every single item in the B tree. Yeah, an example is actually very easy. We have just select everything from dimension customers, and we can put out this, let me get this textual plan here. So let's just output it here. So we see here, this is the textual plan. It's just the same as I showed you before. It's just a clustered index scan on the worldwide importers DW dimension customers table on the primary key, which is the clustered index in this case. So it's a very simple plan, and then if we have a look at the graphical plan here and the estimated plan, you see this is exactly the symbol that I was talking about here. So this is actually nothing fancy. It's a very standard way to retrieve data. Coming now to the more interesting part is the index seek. The index seek, as you see here, let me zoom a little bit. On the icon you see already, it goes down the B tree, so it doesn't go just to the to the most left and then scans everything. As I told you, it looks for this data you really want to have. It is mostly used when the index key is part of the where condition, but this is not the only thing it needs to fulfill. It is also it needs to be sargable, but we come to this later. It's best used when the condition is very restrictive, so we can save a lot of I/O by just pulling out this very data set instead of scanning everything. So if this is the case, we benefit very much from an index seek. And now we come to what I mean. The search, the statement or the parameter you search for has to be you say searchable or searchable argument. It's a searchable argument, and from searchable argument it derives this searchable or whatever you want to call it. You read it in literature quite often. It means your parameters have to fulfill a certain shape, you know, and I will make some examples now. So what is a searchable comparison or a searchable statement condition? So the column equals 3.14 is searchable. No problem with that. We can just go down the index for column 1 and look for this 3.14. If it's there, fine. If it's not there, it's not there. We wasted just this 2 or 3 IOs we used to run down the B tree. A column 1 is like ABC wildcard is also possible because it starts with no wildcard. This is possible because we can just go to ABC in the index and then we have a look what is there and then just range scan everything from that small range. At this point I want to stress very much, if you are not familiar with B trees or clustered indexes or indexes at all, please go watch my other videos on my channel. I have a rather popular video, for my channel at least, explaining how a B tree works and how data is actually stored in a B tree. So go check this out after the live session, or go check it out now and rewatch this session. I don't know what you want to do. And also, of course, the column is greater or equal 22 is also searchable. Because we can just go down again to 22 in the B tree, and then we go to the right from this and search everything from there is in my interest, right? So some examples maybe is good to show also for not searchable arguments. So we have here column 1 plus 1 equals 9. So it is the same as column 1 equals 8, but SQL Server doesn't really calculate that, so it cannot use this as a seek parameter. So although we would have maybe an index on column 1, we would have to search all the columns, and we then have to calculate for each data row column 1 plus 1, and then we decide for each row if it equals 9 or not. This is not very effective. Column 1 equals 8 would be a searchable thing, and we could use the index in column 1. It would be much better. Same goes for this. You see right here, the like was already searchable, but I told you it's only searchable if you don't start with the wildcard, because then you can go to the ABC leaf node that starts with ABC, and then you go to the right and search everything that has something behind it. But if you have something like this, wildcard, test, wildcard, the test can be anywhere. It can be anywhere in any word. You can't really figure out how to search for it. So that's why this is also not searchable, and it would also just utilize here a full table scan or a clustered index scan and evaluate this expression for each row, and then say, okay, here something matches, fine, this is the row, but we cannot really use the index here for index seeking. The same goes for any function that you apply on the column 1. If a column 1 has an index and you apply any function on it, you cannot really utilize the index. This is especially true if you use the, let me write with this one. If you use the isNull function, this is a very popular one for all Oracle viewers here. It is, I think, NVP for Oracle and DB2. So it checks if the first is null, if your argument is null, and if not, if x is null, then y is outputted, else x. Okay, it's very popular. You can also write it with column 1 is not null, then it would be searchable again. But many use functions, and whatever function you use on this, it won't be searchable and eligible for an index seek. So I think we have also a small example for this. Let me show here. Let me show what is this. Let's just check this out. Oh yeah, you can see here this is a more complex example of a query plan. We have an index scan here, column store index scan here, and here we have a join operator here, so you see there are also more complex queries, of course. Where we, by the way, also should have, let me just check this, we should also have, exactly, let me zoom in here, we should also have memory grant info actually on this query, because the hash join actually requires some memory. So here we can see desired memory and required memory. But we want to now have an example for the index, right? So on the customer table, there is no index on the column primary contact. Let's just query this thing again, and you see here we have a column that is called primary contact, and there's no index on it, so we can't utilize it for us, but we can just build an index to demonstrate it. So if there is a leftover index, I just drop it right now. So let's query this table by just asking for the primary contact, this guy here. I don't want to pronounce him really, but let's just do it. Let's just have a look at the actual plan. And we see right here, okay, this is a clustered index scan, meaning we scan all of the rows for the customer dimension, and we then decide for each row, is the primary contact this guy or not, and then we put it to the output. Okay, let's just now create an index on this primary contact column and see what happens. So first of all, you will be a little bit disappointed, or let's actually see what happens. So we go again for here, and we see here, something changed, right? So something changed. We don't have an index scan anymore, but we have, let me just zoom it a little bit, we have the index seek operation here. Okay, but wait, what is this? Index seek, okay, this is good, but what is this? Key lookup and a nested loop join? I didn't do any joins here in this statement. What the heck? So yeah, we come to this just now. This is normal, because you have to think of it. You have now an index on the column primary contact, but we request everything, right? So if we use this index, we can only use it to find the clustered index key for this guy. So now you have to know, and that's why I told you, you have to maybe rewatch the videos about B-trees, that the data is only in the clustered index. In all non-clustered index, we only have the data that we put in here, and we put only primary contact. So what the B-tree looks like, let's just go back to the B-tree real quick. So what our B-tree now looks like is, here are primary contact information in each node. Only this, only information from the primary contact column in this newly created index I did. And here at the leaf level, we of course have the primary contact again, and the clustered, can I write this? The clustered index key. So we have only two information at the leaf level. The primary contact table that we were looking for through the index, and the clustered index key. But we want to know everything about it, right? That's why we have to look this other information up. If we would just, like in this statement, select only the primary contact, where the primary contact is like this, which of course makes not much sense since we already have it here. But just for the sake of demonstration, if we run this, you only see the seek. And you can also see here in the output, when you have it like this, you see here output list. Let me just first zoom it. And then, so you see output list, there's only one column outputting. This is the primary contact. Of course, we don't have anything else in the index but the primary contact and the key. If we now select everything, you see here that, wait, we just hover it first. You see here, whoop, this is live, boys. So zooming, scrolling now. So you see here, we also have the primary contact column that we output. And the only other thing we have in a non-clustered index is the customer key, which is the primary, the clustered index key, the customer key. That's the primary key, right? So those two information are in the index, and those are put out. And now, what? Go away. We need to have all the other columns that are not even in this index. So we need to look it up in the data pages themselves, and we do this by a key lookup. Okay, so next topic is the key lookup. What is even a key lookup? So let's just go really quick to the key lookup. So the key lookup, we saw already the icon is actually a bookmark lookup, but here the actual operator is called a key lookup. So it's the same. If you ever hear bookmark lookup, it's exactly the same. So Jesus Christ, what happens? When does it happen? The key lookup. It happens when a non-clustered index seek is not covering, and this is exactly what just happened. Covering means the index contains all data we need in the select part. And if you just look right here, the index, what is its name? Its name is that we just created here. Its name is ix_dimension_customer_primary contact. It contains only the primary contact information and the customer key, because this is the primary key, but it does not contain all the other information from this table. For instance, filter customer category, buying, and so on and so forth. So we need this information somehow. And this index is not covering. For this query, however, it is covering. We have everything. We could also use the customer key here. It would be still covering, as you can see here. It is still covering because the index contains two columns, the primary contact and the customer key and the leaf level. But for this query, it's not covering. Yeah, there are two possibilities. In order to make it covering, exactly, what do we want to do? Okay, we have to do a seek on the non-clustered index to find the clustered index key. We call it K1 here. Okay, the clustered index key is, in our case, just the customer key. Then the server uses the customer key K1 to do a clustered index seek on the actual clustered index where our data is, to find all the data. We have another example, a second example where we see it more clearly. And this is exactly what we see in this query plan right here. So this one here, this bad boy, is just taking a name, looking for the customer key. Then the customer key is used in this bad boy to actually retrieve the data out of the primary of the clustered key. Of course, we just join them together to make a connection between both of these result sets, but this is an implicit join. We see no join in the query, of course, and then we have our covered row. Mostly SQL Server will do a clustered index scan because joining is more expensive than reading. Yeah, it can happen. We just have a very small table here, but for big tables, if we have the same situation that we have an index on a column, but it's not covering, SQL Server probably won't probably won't do this bookmark lookup with a nested loop term. It may decide that it is cheaper to just forget about the non-clustered index and just take the clustered index information and search for it anyway. Can be faster. But for this very small table, it decided, okay, it's better if we just seek it and we do a key lookup on it. Okay, fine. Okay, fine. Okay, how can we avoid those key lookups? They are not optimal. In big tables, they can be very bad, so we can maybe avoid it. And it is, we have key lookups, and we can avoid them by adding missing columns to the include part of the index. So include would basically mean, if we take our index here, that we include in our non-clustered index, that is our customer key, that is our, what was it? Sorry, I forgot the column name now. What was it? Primary contact. Genau. Exactly. So primary contact, and only in leaf level we have primary contact and we have the customer key. So what and here on those level we have primary contact, and in the root level we have primary contact only. So what would an include do? It would add to the leaf level, so the very low level, other columns like column 1, column 2. Still, we cannot use those columns to search on the index, but we know if we found our data set through the primary contact, we have also access to column 1 and column 2. Then we don't have to do the lookup for those columns. Of course, if we have a nasty query like this, select star, so select everything it makes no sense to add all the columns to the non-clustered index, because then basically what we have is a copy of the table in another index, so it makes really no sense to do this. Exactly. So, but we can make this if we have only 1 or 2 more columns that we want to include. Then we can put an include statement right here, and then we have a cover index. I mean, I actually can demonstrate this. So let's assume we want also to have the category. So we go here for, let's say, customer key, and we go for category. So it is still not covering here because the category is not involved in anything, so we still have the key lookup. But we can just tinker a little bit with our index. We say, okay, the index should be still on primary contact, but please include also the, what was it now? What was it? It was the category. Include the category, please, as well. So let's just drop this, create it. And now let's run this query again, and you see right here it is now a covering index, and we only need the seek. This is actually pretty good because we now get rid of the key lookup and of this join, and it in the end speeds up the query. But we still cannot use it, so if we ask for where category, because the category is now only on leaf level, it is not on root level, we cannot use it for a lookup. So we can category equals, I don't know, something. It cannot be used actually, and it will do in next scan on this, because on a leaf level we still have it. Okay, a second example for this is here. So this is the non-clustered index. The non-clustered index does not have a custom ID. As you can see, it is only on a column called order date, and this is the clustered index. This is where actually all of the data is, all of it. And the clustered index is of course on what is it, on order ID. Okay, so we have a query right here. Select order ID and custom ID from orders. Obviously, orders is a clustered index table with order ID as primary key and primary clustered key, and we have an order date here that we want to filter our result set on this 26th of February 1998. So what the query now does, because the custom ID is not in this non-clustered index. In this non-clustered index we have only on order date. So as I told you, whoa, this was a lag, sorry. So as I told you, the order date is in the leaf level here of the index. We have the order date, and we have here the order ID. Nothing else, no custom ID. So what does SQL Server do? It sees, okay, we have an order date index, so we use it. We just search our way through the index and come to see that the column with our order date, those two for instance, have the key 10908. You can read it right now, 10908 and 10913. With this information we still cannot start outputting our data, because our result set, because we still are missing the custom ID, and the custom ID is not we cannot find in this non-clustered index. So it takes those, sorry, this is not even involved. We take those order IDs, and with it we do the same thing, and we search here in the clustered index with this order ID, because it's built on the order ID, and go down to the leaf level where our data page is containing the whole rows, and there we also find, of course, the custom ID. We find everything there. So this is a second example how SQL Server does a bookmark lookup. It's basically first scanning the actual key entry in a non-clustered index, and then it looks up the data. Basically a lookup table. Okay, so there are two more things I want to cover here in this live session, and those are aggregations, because I want to start with them. Aggregations and group by, exactly. So what does actually a group by do? Of course, maybe many of you know already, a group by basically turns multiple rows to fewer ones, groups them into groups. I mean, I don't know how to describe this better, to be honest. And the group columns define the groups. We will see an example soon. And aggregate functions on top of those group columns, and they define what should happen with the rows that basically get compressed. I mean, if you have 20 rows, and after the group by you have only 2 rows, you basically created 2 groups out of your 20 rows. But what should happen with, for instance, an invoice price or in a number or something like this? What should happen with it? Should we just add everything up? Should we just do an average on it? Should we select the maximum or the minimum? This is the question what we have to ask ourselves in the aggregation function. Exactly. A simple example would be build groups and count how many rows each group has. We can do this right here. We have a simple aggregate for here. Let's see the dimension customer table again. We have, for instance, here the build to customer table. And now I just do a select on build to customer. I just do it like this and omit the other 2 stuff. Then we see only those distinct values on the build to customer. So obviously there are 3 possible values in this column here. NA, this Tailspin Toys head office, and this Winchtip Toys head office. There are no other values in this column right now. So the group by basically says, okay, for all possible distinct values of a build to customer, create a group, and that's it. So now we can toy with it a little bit and add a count to it. And then we see, okay, there's 1 row that has NA in the build to customer. There are 201 rows that have Tailspin Toys, and there are 200 other rows that are Wingtip Toys. So what we can also do now is look again at the customer key. The customer key is just an identity and primary key, but we can also, of course, now say, okay, for each group, please do the sum of the customer key. It makes no much sense here, but I was honestly I didn't really look for a better example right now, but you will get the idea. So NA is obviously has the sum of customer keys 0. So all the customer keys that are in this group obviously summed up are 0. So this would of course imply that only the first row has NA, because the sum of 0 can only happen if you have 0, and the only 0 is here. For the other rows, we see the sum for the Tailspin Toys head office group is 20,301, and the sum of the Wingtip Toys is 60,702. We could also simply just do like this, that we say, give me the minimum of what is the smallest customer key. Let's escape it here, customer key, and then we will have also the minimum for all of this. So the Tailspin Toys head office, the smallest customer key for those rows is the 1, and the smallest customer key is 202 for the Wingtip Toys office. Okay, makes no sense to evaluate this, but just as you know. So this is a group by. It takes basically a bunch of rows, compresses it, chooses a representative for the group that you state here, build to customer for instance, and then outputs your aggregation function, whatever you want to do with it. So we want to know, take a look at it from the query plan perspective. So we saw in a simple example. We have 2 possible ways how SQL Server can actually achieve this. First of all, we have of course to scan all the data. Cluster index scan, for instance, would be very good for this. We retrieve the data, but what then? Another operator has to do the compression, right? To the aggregation. And there are 2 possible ways. The first one is the stream aggregate. The stream aggregate can only be applied if the input is already sorted. There are basically 2 possible ways how you can achieve this. Either there is an index on your group by columns, then we read an index scan of this index would result in a sorted input for the stream aggregation. Or SQL Server can also decide it is okay to explicitly sort the rows before going to the stream aggregation, because it decides, okay, stream aggregation would be still faster. The big bonus thing of this is it consumes almost no memory in the stream aggregate, because it doesn't have to buffer anything. And here's the algorithm. Basically, I copied it from a source, and it's actually very helpful. This is a small look. So we clear the current aggregate results. We clear the current group by columns. Okay, we start blank here. For each input row, we begin. If the input row does not match the current group by columns, then we output the current aggregate results, because we obviously reached the end of a group. We clear the current aggregate results. We see the current group by columns to the input row. We set it, and then we end. If this is not the case, we just update the aggregate result with the input row. So we basically, since we know it's sorted, we know that if the next row we are reading has a different group by value than the previous row, then we know we jumped over a border of groups. We touched a new group, and the old group is finished, and we can output the result of the group we just worked on, and we can start with this group. This is of course a linear thing. We just scan this whole data set once, and then we already could aggregate everything in one situation. That's why we needed the sorted input here. So as an example, this very statement here, we can see, let's just analyze it. We can see here we have a clustered index scan. We know about this one, right? It goes just from down and goes from left to right, scans everything. This output of the scan is giving to a sort. The sort will sort it on the column bill to customer, and the stream aggregate, as I just told you, just takes it and scans through every row and does its aggregation thingy, and output scalars, basically just outputting our sum and our count, which is aggregated in this operator here. So this is the stream aggregation. It's quite a good thing, but the thing is it needs sorted input, and if we have many joins in a statement, many joins, there will, and we use hash join operations, then the input order is not preserved, and we will have some random mix of rows, and then we often can't really do stream aggregations. In big data warehouse queries, it's very unlikely that you have those. It is possible, but it's unlikely. For those cases, we have also a hash aggregation. And if you watched my video about hash joins, then this is basically almost the same thing. So what it does, it builds a hash table. So basically just a table. We have a table, let's say you have a column for the keys, and you have a column for your group values. That's basically a 2-column table. It's a hash table. It's just called like that. The key is are the grouping columns. This is basically your first column in this table, and the second column is basically your partially or fully aggregated result. The big plus is that you don't need sorted input, because the table will will order the values, the keys, in certain buckets, and it doesn't really need to be inserted for this purpose. But it also needs memory. It needs to hold all of the hash table. It cannot just flush the previous result like the stream aggregate. It has to keep everything until everything is read. And for big data warehouse queries, for widespread possibility of key values or of keys, then it can be quite large. And the memory request will be proportional to the number of distinct grouping columns, which makes sense. In the end, you have so many buckets as you have distinct group column values. Makes sense, right? If you have a table where we have, let's say, we have on a column like a category, and we have category A, B, C. And we have many rows that have A, like 200 rows have A and 1000 rows have B. But in the end, the hash table only needs one bucket for A, for B, and C, and just do its aggregation within those buckets. So it is proportional to the number of distinct grouping columns. In contrast, basically, to the hash join, where it is not proportional to the distinct grouping columns, to the distinct number of columns. Yeah, and there's this nasty thing which you also have in hash joins, that you have the spilling. So if memory is not enough, it will spill. What is spill? It will take some buckets, and those get written to a work file in tempdb, so on disk. And it will also include the partially aggregated results, so the bucket and the values that we just choose one and take them out of the table to have some more memory, and put them on tempdb. All rows that would fall in this category, so are not, or also you could also say all rows that are not fitting anymore in the buckets that we have now in memory will also be spilled to disk for a later time. And when this algorithm is done the first time, it will just be put the spilled buckets to the memory and the already aggregated ones down to tempdb. It will basically swap and then do the calculation again with that rows that got spilled. It's nasty, and it's especially nasty when you consider hash joins can slow down quite a bit, especially if the estimation for your memory was bad or you don't have so much memory, then when spilling is mandatory. Okay, we can also see an example for this. Here we can just force the whole query to use the hash group and not the stream aggregation. If we do it like this, of course we have the same results, but you see here that we have another execution plan, a different one. So we have still the clustered index scan, since we need to feed the aggregation operation somehow the rows. And here you see no sort anymore. You see just the hash aggregation. You can also see, like, if you compare those two, if you have a look at like memory grant info, we have here requested memory. Granted memories, okay, 1040 kilobytes of granted memory, and if we run it with stream aggregation, we need memory for sorting, but not for the stream aggregation itself. And for sorting, it took actually also 1024, but the desired memory and the requested memory was lower, so it decided that it would be better. In the end, it's still the same, and it's a very small table, and of course you don't see so much difference. But you see, for bigger tables, almost always hash aggregation, since sorting a big input is very expensive, and if you select too many columns, you can't really put a good index on it. It will also result in just taking everything, and therefore just a hash aggregation. So these are basically the two only things how it can aggregate, and it's the only thing. Either we sort it or have it sorted from some index and we do a stream aggregation, or we do it like this, that we just take everything and put it into the big hash table. Those are the only options. I don't know why this is open now twice, but okay. Let me just say one last thing and then I'm finished with this live stream for once. For now, I mean, distinct versus group by. You often hear opinions from coworkers or from so-called experts that say, okay, distinct is much better or much worse than a group by. You should always use this because. And I have to admit, there are DMBMS out there that handle distinct and group by completely different. But for SQL Server, it's not the case. So group by and distinct use either stream aggregate or hash aggregate. There are no other options. And for SQL Server, a distinct is just a group by without any aggregation function. You can see this by just typing in a simple query on your table of your wish and do a group by, and you do a distinct. You see the exact same plan. SQL Server doesn't really care. It only cares if the import is sorted or if it can be made available sorted easily or not. And then it decides to do a stream aggregate or otherwise a hash aggregate. So it does really not care if it's distinct or group by, so those are really not different at all. What is the conclusion of this first test session I did with you? So visual query plans we read from the right to the left and from the top to the from top to bottom. Okay, we have to keep that in mind. Each node needs input from all predecessors. We saw this. The scan operator outputs some rows, and the sort operator takes it and outputs some rows in a sorted way. Then the stream aggregate comes and takes it into takes those rows and outputs only the groups that we want, and so on and so forth, all up to the select node. The leave nodes, the nodes that actually read the data. I mean not in a table. I mean in this. Let's say this is a graph, then this is the root node and this is the leaf node, right? Okay, the leaves point upwards to the root, but you have to look at it like this. Then the leaf nodes are always the retrieval operators, right? The one that get the data, and it can only be a clustered or a normal index scan, a clustered or an index scan. What I didn't mention, right? yet is a heap. It can also be a table scan. A table scan is for just a heap where we have no clustered index at all. And it can be a key lookup if we're talking about clustered indexes, or on heaps it's called a row identifier or RID lookup, but it's the exact same thing. So for our purpose it's not necessary to look at heaps, it's the same thing. Then we talked about aggregations. Yeah, I know since this is the very first session, nobody knew that I would stream. I have only 1 or 2 viewers here right now, so no interaction was there, so I knew what to put on conclusion. We have 2 possible aggregates: stream for pre-sorted input and hash for unsorted input. That's basically what you can take away from it. And what is really important to me, because I heard it often at work, distinct and group by is not different, is exactly the same. So this is basically it. I thank you very much for checking out this session. I will of course upload it also to YouTube, so that you can have a look at the session offline. It will be a little bit longer, and I will, if you want to do it, I will do such live sessions also more regularly if you like it. Otherwise I will just stick to my normal videos. So I wish you still a nice Sunday evening if you're here in Europe, and chill out a little bit. Tomorrow is work day, right? So bye, and have fun.